now that we know how to solve systems of linear inequalities, we can move on to what we really want to do, which is solve linear programming problems. So we're going to restrict ourselves to just 2 dimensions, and over the next few sections we'll be really solving linear programming problems, but today we'll take what's called a geometric approach to solving them. So what I have written behind me is a general definition of what linear programming is. There's a lot of words here, but I've written it all up so that we can go through some of the terminology. So I'll just read through it. A linear programming problem is one that's concerned with finding the optimal value of a given function. So by optimal value, I mean a maximum or minimum value. We want to make this function that we're given as big as possible or as small as possible. So it's concerned with finding the optimal value of a linear, so it's got to be linear and non-zero. It can't just equal constantly 0. A linear non-zero objective function z. So this function that we're trying to maximize or minimize, we call this the objective function. It's got 2 decision variables, just means it's a function of 2 variables, x and y. We call these variables decision variables. So our function generally looks like this. Z is equal to ax plus by. Alright, so where a and b are constants. Subject to problem constraints, and the problem constraints are just a system of linear inequalities. Alright, so there's more terminology. The problem constraints are a given system of linear inequalities, and we have to have that our system of linear inequalities contains the non-zero or non-negative constraints. X is bigger than 0, y is bigger than or equal to 0. If we don't have those, we have to throw them in. And any point in the resultant feasible region that produces the optimal value of the objective function is called an optimal solution. This is what we're looking for in linear programming. So generally, just to recap, again, there's a bunch of terminology, decision variables, objective functions, and so on. But what we're given is we're given a function like this. We're given a function like this, z equals ax plus by. There's our objective function. It's a linear function of 2 variables. And we're given a whole bunch of problem constraints, and this consists of a system of linear inequalities that has to have the non-negative constraints. X is bigger than or equal to 0, y is bigger than or equal to 0. So we're given this a linear function. We're given a bunch of a system of linear inequalities that gives us a feasible region. And the question is, what point in that feasible region makes this function as big as possible? And what point in that feasible region makes this function as small as possible? They don't always exist, but if they do, we call those points optimal solutions to the linear programming problem at hand. And I think the best way to describe this further, or explain this further, is just to start going through examples. So we'll proceed with that. Alright, so what I have behind me is a typical linear programming problem. So the question is, maximize and minimize this function, z equals 2x plus 2y. This is the type of function we'll be looking at. So this is a linear function of 2 variables x and y, where a is equal to 2 and b is equal to 2. So this is our objective function, using the terminology from the board of words that I just erased. So this is our, objective function. Here's the function we want to find optimal solutions to. And we have our problem constraints here, subject to this system of linear inequalities. It's a pretty big system, and it has these non-negative constraints that we have to have. X is bigger than or equal to 0, and y is bigger than or equal to 0. So this is the problem constraints. So how do we actually solve this problem? How do we solve linear programming problems using a geometric approach, as we're going to do today? I will give you a full algorithm after we do this example. I just want to sort of go through the example. And the good news is it really mostly comes down to understanding the feasible region. So all I really have to do is exactly what we were doing in the last section, which is find the solution set or the feasible region for this system given by our problem constraints. So here's what we'll do. Graph the feasible region. Alright, let's work with these one at a time. Equation 1. What do I have to do to graph that linear inequality? Well, I have to understand the boundary line and which half plane we're looking at. So let's just go. Equation 1, the boundary line is going to be 2x plus y equals 20. And if I solve for y, that's y is equal to minus 2x plus 20. Alright, so what is that? That's a line with slope -2 and y-intercept of 20. Sorry, I'm just looking at these other lines really quickly. Okay, so I'll put 20 right here. And it has slope -2, so y is 0 and x is 10. So I'll just undraw this portion of it. There we go. So this is line number 1. And I'm only drawing this portion of it because, again, we only care about what happens in the first quadrant because of these non-negative constraints. And I have to decide which half plane I'm looking at. Am I looking at this side or this side? So let's see, let's try plugging in the origin into this function. 2x plus y, if I plug in x equals 0 and y equals 0, I get 0 on the left. Is that less than or equal to 20? It is, so the origin lies in the half plane that is the graph of this function. So we are looking at this side. All right, so this line, that's number 1. Now we'll work with equation number 2. Equation number 2. Oh boy, I think I'm probably going to have to redraw this, but we'll keep going here. Not because it's wrong, just because the scale is going to be all messed up. We've got 10x plus y is equal to 36 to get our boundary line. That means y is equal to minus 10x plus 36. Alright, so that's up here somewhere. 36 is up here. Has slope -10. So y is going to be 0 when x is actually 3.6. I don't think I need the number 3.6, I just need to illustrate the fact that this is very steep. Okay, so there's line number 2. Once again, I have to ask which half plane I'm looking at. Well, let's see. We'll plug in the origin once again. We'll plug in 0, 0. If I plug in 0, 0, x equals 0, y equals 0, I get 0 is bigger than or equal to 36. That is not true, so we're not looking at this side. We're not looking at this side of this plane. We are looking at this side. Maybe I can do it in the color. How about we go yellow? Okay, last but not least, boundary line number 3. We have third equation here. We have 2x plus 5y is equal to 36. Go ahead and solve for y. 5y is equal to minus 2x plus 36. So y is equal to minus 2/5 x plus 36 over 5. 36 over 5, what is that? That's a little bit bigger than 7. 7 and 1/5. So somewhere way down here. It's 36/5. I don't think I need that fact though. It has a slightly negative slope, so it's almost horizontal, just very slightly negative. Looks something like this. And what side of this line am I looking at? So here's boundary line number 3. What side of this line am I looking at? Again, take any point not on this line, so we'll take the origin. Plug in 0, 0, I get 0 is bigger than 36. That's not true, so I'm looking at everything above this line. So what's the overlap of all these regions? The overlap of all these regions, everything to the left of this line, no. We were to the left of this line, right? So everything in white below this guy, everything in red above this line, and everything in yellow to the right of this line. The overlap region is this triangle right here. Okay, so like I was saying, I'm not a big fan of this drawing. Let me redraw this very quickly. But yeah, I'll just redraw it very quickly so that it looks a little bit better. Okay, so what tends to happen when you're drawing these pictures is you have all these overlapping planes, lots of stuff shaded. It results in a very complicated or very busy image. So I've just redrawn our image here. Here's my 3 boundary lines, and here's the overlapping region. Okay, so there's our feasible region. We won't worry about the objective function just yet. Turns out what's really important with your feasible regions is the corner points. We found corner points last time. We'll just do this again quickly because we want all of the corner points. So we'll find the corner points. This first one, it's nice to sort of label your boundary lines so you know which ones are which. This first point here is the intersection of boundary line number 1 and number 2. So we'll set them equal to each other. Unfortunately, I erased what they were. Boundary line number 1 is y equals minus 2x plus 20. Boundary line number 2 is y equals minus 10x plus 36. So setting them equal to each other, we've got minus 2x plus 20 equals minus 10x plus 36. And solving for x here, let's add 10x to both sides. 8x is equal to, subtract 20 from both sides, is equal to 16. So x, of course, equals 2. And if x equals 2, plug in x equals 2 into either one of these, that would mean y is minus 4 plus 20 is 16. So 2 and 16. That point right there, 2, 16. All right, how about we do corner point number, well, I haven't numbered them, but we'll do this corner point right here now. That's the intersection of boundary line number 2 and number 3. So boundary line number 3 I've erased, but it was y is equal to minus 2/5 x plus 36 over 5. So we'll equate lines 2 and 3. We've got equating lines 2 and 3, we're looking at minus 10x plus 36 equals minus 2/5 x plus 36/5. I want to solve for x, so I'm going to multiply both sides by 5. Unfortunately, these numbers are kind of big, but multiplying both sides by 5, I'm looking at minus 50x plus 36 times 5. 30 times 5 is 150. 6 times 5 is 30, so 36 times 5 is 180. Minus, oops, don't have quite enough space, equals minus 2x plus 36, right? Multiplying both sides by 5. So let's see, let's add 40x to both sides so we can keep it positive. So over here we're looking at, we're adding 50x to both sides. 50x minus 2x is 48x. And subtracting 36 from both sides leaves us with 144. And that 144 is just 48 times 3, so x is equal to 3 when we divide both sides by 48. Cool, so what's y? Well, plug y into either one of these equations. What are we working with? We're doing the intersection of 2 and 3. So plug x equals 3 into equation 2, and we've got y is minus 30 plus 36 is 6. So this corner point here is 3 and 6. Looks like a reasonable number. I would expect it to be just a little bit to the right of the x value of the one above it. So this was x value 2, this is x value 3. And This guy, I'm expecting, of course, a bigger x value again, and a y value slightly smaller than 6. So we just have to find this last corner point now. And we are working with the intersection of 1 and 3. So we'll equate minus 2x equals 20 to equation 3 minus 2/5 x plus 36 over 5. Once again, oops, this is a plus 20. Once again, I want to multiply both sides by 5, so we're looking at minus 10x plus 100 is equal to minus 2x plus 36. Add 10x to both sides, so we've got 8x over here. Subtract 36 from both sides, and we're looking at 64. 8 goes into 64 8 times, so this is x equals 8. Again, I was expecting something bigger than 3, and I should have a y value a little bit smaller than 6. Plug y equals 8 into either one of these equations. I'll plug it into equation 1 because there's no fractions. If x equals 8, y is going to be minus 16 plus 20, which is 4. So finally, this corner point is 8/4. So far, I've done nothing new. This is everything we were doing in the last section, graphing feasible regions given a system of linear inequalities. Now we're going to do something new. Now I want to maximize or minimize. I actually want to do both because it asks us to do both. I want to find optimal values for this objective function. How am I going to do that? Well, the good news is the algorithm. The algorithm we're going to use tells us that these optimal values only occur at corner points. They could actually possibly occur all the way down the side, but they always at least occur at the corner points. So all you really have to do is evaluate this function at the corner points. But in this example, I want to explain to you why that's true. And a few of the homework questions will actually ask you to find the maximum or minimum using the method I'm about to illustrate right now. So here's our objective function. It's z equals 2x plus 2y. I want to find points in the plane with coordinates x and y that when I plug them into this function, this makes this function as large as possible and as small as possible. Well, of course, if I want this to be as big as possible, you would just take x and y to be as big as possible, right? You just take huge values for x and y, that makes that function really big. But we want to do something more complicated than that. I want to find points that live only in this feasible region. Which points in this feasible region make that function as big as possible? So how are we going to proceed? Well, let's fix this to be a constant value. So let's fix maybe z equals 0. All right. So fix z to be constant values. So how about I do z equals 0? What do you get? You get 0 equals 2x plus 2y. Or rather, what does that mean y equals? 2y is minus 2x, so y is minus x. How about z equals 1? If z equals 1, I get 1 equals 2x plus 2y. Or if you solve for y, that would be y equals minus x plus 1/2. How about I do z equals 2? Z equals 2, I get 2 equals 2x plus 2y, or y equals minus x plus 1. So hopefully you can see what's happening here. This z value, if I fix it to be a constant value, all that's doing is changing this constant at the end here, right? If z is 1, I had minus x plus 0, or sorry, if z was 0, I had minus x plus 0. If z was 1, I had minus x plus 1/2. Then z is 2, I had minus x plus 2/2. Z is 3, I'd have minus x plus 3/2. Z is 4, I'd have minus x plus 4/2 over 2. So if I graph these things, y equals minus x, what is that? Y equals minus x is just this line. That's if z equals 0. Y equals minus x plus 1/2, so when z is 1, well that's just this line, but shifted vertically up half a unit. Right? So take this same line, parallel to it, shift it up half a unit. There's z equals 1. Take z equals 2. Z equals 2 takes that whole thing, shifts it up half a unit. There's z equals 2. Well, if I graph them all, here's z equals 3, z equals 4, z equals 5. Roughly, I'm not claiming this is to scale, but if you draw these lines, these sort of constant value lines for z, you would get this picture. So z is increasing as we step up these constant value lines, right? So you can sort of see the point in this feasible region that's going to give the biggest value for z would be the point that lies on this largest constant value line for z. Well, which point lies sort of furthest up this vertical step ladder? This point right here. Right, say this was z is 2, there's z is 3, there's z equals 4. Well, this point looks like it gives the values even slightly bigger than z equals 4, but it's clearly corresponding to the largest value for z. Again, I'm not claiming these are to scale. This might be z equals 10 or something, I don't know. But as we proceed further and further up these constant value lines, you'll see where we eventually hit this corner point, which is the very last point in this feasible region that gives us the largest value for z. Similarly, if I want the smallest value for z, we'll progress down this step ladder. Progress it down this step ladder because these values for z are getting smaller as I push downwards, and the point that lies on the smallest constant value line for z would be this corner point right here. Right? It's not this one because this one is on a slightly larger constant value line. So z is slightly larger along this line than it is along this line. So this corner point right here, that gives me the maximum value, and this corner point right here, that gives me a minimum value. And if you think about this, this is always going to happen. So if I want to maximize or minimize objective functions, the maximum or minimum, if I sort of graph these constant value lines, think about it and you'll realize that the smallest value for z always occurs at a corner point, and the biggest value for z always occurs at the corner point, or at a corner point. There's one exception. One exception would be if these constant value lines lie parallel, if they lay parallel to one of these boundary lines, then you could actually have an optimal value occurring sort of at two corner points that are joined by the same line, and an optimal value along that entire boundary line. That could happen. I won't do any examples like that, but it doesn't really matter because you still have an optimal value at the two corner points. So all I have to do now is find the value of the function of the corner points. So we have at 216, z is going to equal 2 times 2 plus 2 times 16, which is 2 times 16, 32, plus 4 is 36. That is the maximum value of this function in this feasible set. And at the other corner point we observed, 3 and 6, we have z is 2 times 3 plus 2 times 6, which is 6 plus 12 is 18. And there's the minimum. Alright, so if you plugged in any other point in this feasible set, any other point at all, you would get a value somewhere between 18 and 36, because 18 is the actual minimum of this function in this triangular feasible region, and 36 is the actual maximum. Justified using these constant value lines, but we're not going to draw constant value lines anymore. we're just going to go with the observation that maxes and mins have to occur at corner points. So the algorithm is going to be find all the corner points, plug all the corner points into the objective function, and the largest value will be the maximum, assuming a maximum exists. I'll tell you exactly when it does in the algorithm. And the smallest value we attain is going to be the minimum, assuming a minimum exists. And again, I'll show you exactly when that happens. Here's the geometric method for solving linear programming problems. It's really just two steps. One is graph the feasible region. Alright, so just graph the feasible region. This is what we've been doing with the entire last section. Take your problem constraints, this is a system of linear inequalities, graph the feasible region. One, if the feasible region is bounded, so we talked about bounded and unbounded feasible regions last time. If the feasible region is bounded, then you're guaranteed that a maximum and minimum always exist, and you can proceed and find them. If the feasible region is empty, this can happen, then a maximum and minimum don't exist. You can stop. You can just say they don't exist, and you can stop doing the problem. They don't exist, you're done. And the third case is if the feasible region is unbounded, so this could happen, you could have an unbounded feasible region, and the coefficients of the objective function are positive, then only a minimum value exists. You can say a maximum doesn't exist, and you can proceed and find the minimum value. If you're in a situation where, say, the feasible region was unbounded and your coefficients were negative or something, or one of the coefficients were negative, then neither would exist, right? Because a minimum exists only if you're unbounded and the coefficients are positive. Okay, so you make these three decisions, right? You graph your feasible region, you go through these three decisions, and you ask, does a minimum exist, does a maximum exist, and if they do, you go ahead and find them. And the way you find them is once you've understood your feasible region, you would find all the corner points. Find all the corner points and plug them into the original objective function. The largest value that you find is the maximum value, assuming a max actually exists by this decision tree here. And the smallest value you find, so you plug in your corner points and you get values for the objective function. The smallest value you find is the minimum, assuming, once again, you've gone through this decision tree and you've decided that a minimum must exist. Then the minimum value you find is the actual minimum. As you're going through homework problems, I believe they describe this process as building a corner point table. So you've got a table with all the corner points and all the values of the function, the objective function. So we'll build these tables as we do these problems, but this is what they usually call this. So step number 2, they call this building a corner point table. And with that, now that we have an algorithm, we'll do another example. Alright, so here's our example. Standard linear programming problem. Maximize or minimize the following objective function, z equals 20x plus 5y, subject to this system of linear inequalities. And again, my system has the non-negative constraints, x and y have to be bigger than or equal to 0. So step number 1, understand the feasible region. We need to go ahead and graph all of this stuff. So I've got three boundary lines here, 1, 2, and 3. So let's see, boundary lines. Number 1, if I solve for y, I would get y equals minus 6x over 2, so minus 3x, plus 36 over 2 is 18. Boundary line number 2, solve for y, I get y equals minus 2x over 4, so minus 1/2 x, plus 32 over 4 is 8. And boundary line number 3 is, of course, just y equals 20. So we'll graph all three of these. Y equals 20 is easy, that's just up here. There's boundary line number 3, 20. Again, just erasing this part because I only care about the first quadrant. There's boundary line number 3. Boundary line number 1, y-intercept 18, slope minus 3. So that's going to go from 18, slope minus 3, y is 0 and x is 3. So 18 to 3. Right here. This is boundary line number 1. And then we've got boundary line number 2, slope minus 1/2, y-intercept of 8. So here's 8. And with slope 1/2, x is going to be 16 when y is 0. So something like this. 16, there's boundary line number 2. So what are we looking at? We want to be below y equals 20, right? Because we want y to be less than or equal to 20. Again, you could formally just plug in a point, plug in the origin, 0, 0. That satisfies the equation, but y less than 20 is easily understood to just be everything less than this line. So we're below this line. What about equation number 1? The origin is not on this line, so we'll plug in the origin. 0, 0. So is 0 bigger than or equal to 36? It is not. So we're not looking at this side of the line, we're looking at this side. And again, plug in the origin 0, 0 into the second equation. Is 0 bigger than 32? It is not, so we're looking at everything on this side of this line. So our feasible region, the overlap of all of that stuff, everything above this line, everything above this line, and everything below this line gives us this shaded region here. Now you have to go through your decision tree. Now that you understand what the feasible region looks like, ask yourself, is this bounded? It is not, right? It extends off to infinity in this direction. No circle I draw can ever encompass this. It's not bounded, therefore a maximum is not going to exist. So unbounded, which means no max. But I could still have a minimum. I just have to ask, are the coefficients to my objective function, are they positive? The answer is yes, they're both 20 and 5. Unbounded, but I do have positive coefficients. So we do have a minimum. So we're going to keep going with the problem. If I had no minimum as well, I would state that. No max exists, no min exists, and we'd be done. But I know a minimum exists, so we'll keep going. We'll find the minimum. And to do this, I need to find my corner points. This one's very easy. That's just, there's a corner point. That's just 0 and 20. This one's very easy. That's a corner point. That's just 0 and 18. This one's very easy. There's a corner point. That's just 16 and 0. So the only corner point that's going to give me some trouble is this one. We have to find that. Okay, so what do I want to do? I want to figure out when a boundary line number 1 intersects boundary line number 2. So we'll set minus 3x equal, or plus 18 equal to minus 1/2 x plus 8. We'll solve for x. Probably multiply both sides by 2, so minus 6x plus 36 equals minus x plus 16. Let's add 5x to both sides, or 6x to both sides to get 5x over here. Subtract 16 from both sides to get 20 over here. And this, of course, gives me x is 4. If x is 4, plugging back into either one of these equations, if x is 4, y is going to be minus 12 plus 18 is 6. So this point right here I have 4 and 6, but I claimed 3 was right here. This should be something smaller than 4. Here's the mistake, right? You should always catch yourself. I should not have labeled this as 3. When is y equal to 0 for this line? Y is equal to 0 when x is 6. Right, an accurate drawing can, if this was 3 and this had an x coordinate 4, that would have been very confusing. So this is 4 and 6 now. That makes more sense. Okay, so here's all of my corner points. So we're going to build the so-called corner point table. point, and here's my objective function, z equals 20x plus 5y, and we're just going to plug them all in. So I've got corner point of 0 and 20, I've got a corner point of 0 and 18, I've got a corner point of 4 and 6, and I have a corner point of 16 and 0. These are the only places that optimal values can occur. They could also, actually occur all the way down the sides, but if they occur there, they're the exact same values they are at the corner points. So we can restrict ourselves to just looking at the corner points. And now I just have to plug these points into the objective function. So 0 and 20. X equals 0. I have 20 times 0 is 0, plus 5 times 20 is 100. 0 and 18, I have 0 plus 5 times 18. 5 times 18 is 90. Let's skip this one for a second. 16 and 0. 20 times 16 is, 10 times 16 is 160. So 20 times 16 is 320. Plus 5 times 0, so here I have 320. And last but not least, 4 and 6, plug in 4. I've got 20 times 4 is 80. Plus 6 times 5, 80 plus 30 is 110. This is why it's really important to identify, before you do your corner point table, do maxes exist and do minimums exist? Because you might look at this table and say, well, 320 is the biggest value I found, therefore that's the maximum value of my objective function in this region, but maxes don't exist. Right? The max is actually somewhere way, way out here. Well, there is no max, but the objective function keeps getting bigger as you go way, way, way out here. So there is no maximum, but if I look at the smallest value, this guy, I've already observed that a minimum does exist. The smallest value in this list is the minimum, so it's 90. So the minimum value of z is 90. Where does it occur? It occurs at 0 and 18. So occurring at the point 0, 18. And that is a typical linear programming question. This is the two steps that it comes down to. Most of the work is understanding your feasible region. Understand the feasible region. This is what we've been doing for the last 2 sections. And the only other step is, now that you understand it, ask yourself, does a max and min exist, going through that decision tree? And if they do, well, figure out where the max and min occur by plotting all the corner points, evaluating the function of the corner points, and the smallest value if a minimum exists is the minimum. The largest value if a maximum exists is the maximum. Here we didn't have a maximum. There's one more thing that makes these questions kind of hard, is now actually doing real-world applications. So we'll set up a real-world application problem, and from there it will become a standard linear programming question. So here's a typical linear programming question, and this is where these can kind of get a little bit more difficult, is because it's a real-world application, it's essentially a word problem if you want. We have to build the objective function and the problem constraints ourselves. Once we've done that, it will become exactly what we've been doing, but we have to take all of this information and model this ourselves. All right, so we have to build up a mathematical model. So here's the entire problem. There's a lot of stuff here, but a chicken farmer can buy 2 different types of food mix. He's got type A at 20 cents a pound and type B at 40 cents per pound. And there's different nutritional profiles for each of these mixes. Each pound of mix A contains 3,000 units of this nutrient N1 and 1,000 units of nutrient N2. Meanwhile, each pound of mix B contains 4,000 units of both of these nutrients, 4,000 units of N1, 4,000 units of N2. All right, so then we're given the daily nutritional requirements of chickens, at least these chickens. they need 36,000 units of N1 and 20,000 units of N2. So the question is, how many pounds of each food mix should he be giving these chickens to minimize his cost? To minimize, the daily food costs for his chickens. Well, by the way, so I should say that, so you need to meet these daily nutritional requirements, or you can exceed them. Hence, we're going to have some inequalities here. You can go over these minimum daily requirements, that's no problem. But, so what do we want to do? Well, remember we had this term for our variables x and y. We call them decision variables. It's because it's what we're deciding on. So what is our decision here? Well, our decision is how much of each mix to feed these chickens, right? How much of mix A to give them, how much of mix B to give them. So our decision variables, I need to come up with some variables in the problem. The decision variables A will be the number of pounds of mix A, and B will be the number of pounds of mix B. And what do we want to optimize? We want to minimize the daily food costs. So that now, this is what you should always do. You should read your problem, ask yourself, what am I trying to optimize? What am I trying to maximize or minimize? I want to minimize daily food costs. So let's come up with a function for daily food costs. We'll call it C for cost. And based on my decision variables A and B. Well, if I decide to give my chickens 80 pounds of mix A, that's going to cost me 20 cents per pound. So I'll just convert this to dollars. 20 cents is 0.2 times A. And if I decide to give them B pounds of mix B, that's going to cost me 40 cents per pound. So the total sum, the total cost would be 20 cents times A plus 40 cents, or $0.4, times B. Alright, so now you choose A and B. You choose number of pounds for A, number of pounds for B, plug that into this function. That would give us the daily cost. This is our objective function. Now, what are my problem constraints? Well, my constraints are that no matter what values for A and B I choose, the number of units of nutrient N1 has to be at least 36,000, and the number of units of nutrient N2 has to be at least 20,000. So if I choose A pounds of mix A and B pounds of mix B, how many units of nutrient N1 are they going to get? Well, per pound of A, they're going to get 3,000 units of N1. So we've also got 3,000 times A, plus per pound of mix B, we've got 4,000 units of nutrient N1. So you choose values for A and B. The number of units of nutrient N1 they get is going to be 3,000 times A plus 4,000 times B. I need that to be at least as big as 36,000. And so I do have this constraint. I have this constraint on my nutrient N1. No matter how I choose A and B, I need this sum, which is the number of nutrient, or the units of N1 that they get. I need that to be at least as big as 36,000. We can do the same thing with N2. If I choose N pounds of A, they only get 1,000 units of N2. And they get 4,000 units of N2 from mix B. So the total number of units of N2 they get based on values for A and B that we choose would be 1,000 times A plus 4,000 times B. I need that to be at least as big as 20,000. So those are our only two sort of constraints that we're given, but remember we always need our non-negative constraints, and the way this works into a real-world problem is, of course, I can't give them negative units of food, right? I can't give them minus 10 pounds of special mix A. So we also have that A and B have to be at least as big as 0. And this is it. This is our problem constraints. And this is probably what you'll find the hardest part of linear programming problems, taking these word problems, taking this and building a mathematical model for it. The more you do them, the better you get. But again, I tried to make this sort of feel a bit algorithmic, and then ask yourself, what are you deciding on? In this case, we're deciding on how many pounds of A and B we're using. So make those your decision variables. Ask yourself what you're trying to maximize or minimize. Once you do that, you build the function that you're trying to maximize or minimize. That gives you your objective function. And last but not least, try to come up with your constraints. Ask yourself, what are your constraints? And in this case, our constraints are the fact that we need N1 to be at least 36,000, and we need N2 to be at least 20,000. So based on A and B, how many units of N1 and N2 are we getting? Well, we build a model for that as well. So that's the hard part, but now that we built this, we can essentially erase all the words. Right? We've built a mathematical model. We don't need the words anymore. I suppose maybe we should remember the units. Units are pounds, and this is in dollars now. I convert those to dollars. But now you go ahead and you solve this linear programming problem. I will skip ahead. I will leave the details to you solving this particular problem. What do? You build the feasible region. I'll just tell you what the feasible region is. My variables here are A and B, not X and Y, so I'm just going to call this the A-axis and the B-axis. But if you sketch your feasible region, you get something like this. 9, 12, 5, and 20. And this corner point right here is 8 and 3. So our feasible region is unbounded, therefore no maximum exists. That should not come as a surprise. We can just we can buy as much mix A as we want, as much mix B as we want, and just feed our chickens infinite amounts of food, I guess, and that would, of course, raise our cost to infinite levels. But it's unbounded, but because these coefficients 0.2 and 0.4 are both positive, we know a minimum exists, and the minimum is going to exist either at this corner point, or this corner point. So we'll just make a corner point table really quickly. Corner point table. Here's the cost function, 0.2 times A plus 0.4 times B. And our corner points are 0 and 9, 8 and 3, and 20 and 0. Plug them into this function. Remember, the first coordinate is A, the second coordinate is B. So plugging into this function, I'm going to have 0 plus 0.4 times 9 is $3.6. 8 and 3, plug that in. I've got 1.6 plus 1.2 is $2.8. Sounds right to me. And plugging in 20 and 0, 0.2 times 20 is 4 plus 0 is $4. So the mix that gives us the minimum cost is 8 pounds of mix A, 3 pounds of mix B for $2.8 a day. So the minimum cost results from 8 pounds mix A plus 3 pounds mix B for $2.8 per day. So we skipped all the work. We've already solved a few of these systems, a few of these linear programming problems. So we skipped all the work in sketching the feasible region. But go through it and sketch the feasible region. You should get this. And from here, it's just a matter of, okay, I know a minimum exists. I'm going to evaluate the function, the cost function, all the corner points. The smallest value I find is the actual minimum value. These tend to take practice. If you want to see a few more examples, the book has a few more examples done. There's other videos you can watch to see more examples of converting converting these word problems to actual mathematical models, but ultimately the more you do them, the better you get. So read through the textbook if you want to see more examples, but we'll stop here. Thanks.